Hello, the next equation that we're going to be using has what's called thermal conductivity in it. And this is the rate at which heat will flow through an object based on the thermal conductivity, which is K. This depends on what the material, or what the wall or whatever it is we're looking at, what it's made out of. There's a thermal conductivity for steel, for styrofoam, for all kinds of things. The higher the conductivity, the better a conductor it is, and the better a conductor it is, the worse an insulator it is. A is the area of the wall or whatever it is that we're looking at. Delta T is the difference in temperature between the inside of the wall and the outside of the wall. Okay? And L is the thickness of the wall. So when we're dealing with thermal conductivity, this just depends on what the material is made out of. It doesn't depend on how much there is. We've got to plug that in separate here with the L. And with this we'll be using all metric units. So here we've got the thermal. We want to calculate the rate of thermal energy transfer of a wall that's 2 meters by 1 meter by 0.04 meters thick. The wall has a thermal conductivity, or K, of 0.1. Now look at the units on that. It's the joules and seconds and meters and degrees C. So we want our lengths and thicknesses in meters, which they are, and we want our temperatures in degrees C, which they are. If there's 10 degrees on C on one side of the wall and 5 degrees C on the other, and then figure out how much energy was lost after an hour. So what we want to do is use this equation here to figure out the rate at which we're losing energy. And then we'll use this equation here. Power is equal to the energy transferred divided by the time. This is the rate at which energy is transferred. So we use this to figure out the total amount of energy that was transferred after a certain amount of time. So we want to figure out that after 1 hour. So list what we know. We know the area is 2 meter by 1 meter. We're given that K is equal to 0.1. We've got L is 0.04, which is the thickness of the material. We've got delta T is going to be the 5, because it's 5 degrees different on the inside and outside. And the time is going to be 1 hour, also known as 3,600 seconds. Okay, so at this point we want to plug into an equation. P equals Ka delta T over L. So plug in the numbers: 0.1 for K, 2 for A, 5 degrees C for delta T, and 0.04 for L. Just plug and chug. And we get that the rate at which we're losing heat or transferring heat is 2.5 watts, or 2.5 joules per second. A watt is also known as a joule per second. Okay, so to figure out the actual total amount of heat, we're going to use this equation, where P is equal to the number we just found. That's the 2.5 watts. Delta T is equal to the 3,600, and Q is the total energy. That's what we're looking for. And for some reason that doesn't pop up, but I thought basically Q is equal to P times delta T. Q is equal to P times delta T, cross multiply. P is 2.5, delta T is 3,600, multiply them, and that's total energy transferred. Okay, so that's one way of talking about how good a wall section will transfer heat, or how good it will resist transferring heat. The other way we can look at it is through what's called the coefficient of thermal conductivity, sometimes called the U factor, and its related term, the R factor, which is very commonly used. The R factor is used really common in everyday construction kind of lingo. So the power is equal to the thermal coefficient of heat conductivity. Okay, coefficient of heat conductivity. And the previous one was thermal conductivity. So they're really related, or they're really similar, but they are different. So this is the area of the wall, which is just like before, and this has got delta T in it, which is the temperature difference on one side of the wall versus the other. Notice that the thickness of the wall is left out. That's because this U factor takes into account the thickness of it. So there'll be a U factor for an inch of the material, and it'll have twice the U factor for 2 inches of the material. So you don't have to worry about that. Now, if we're more interested in how good it is of resisting heat transfer, which if we're insulating our walls and that kind of thing, we're more interested in the R value, which is basically it's just 1 over the U factor, the U value, the coefficient of thermal conductivity, coefficient of heat conductivity. I get them confused too. So now, when you want to figure out the R value of a wall, what you do is you just look at what each of the wall components is made out of, and you add the R values together. So drywall is in most newer houses walls, or by most I mean all. So it's got an R value of 0.45, which is not real high. If we go to some actual insulations, you get R values. This is just for 1 inch. It's got an R value of 7, which is pretty good. Brick and some things have R values. They're not great, but they do have R values. Your fiberglass bat. Now this is given in per inch. Okay, so remember I said that I already took into account the R value. I already took into account the thickness. This is a caveat. This R value is given per inch. So if you've got 10 inches of this stuff, which would be quite a bit of insulation, you'd have an R value of 31.42. Which, if you're looking in the attic of a newer house, that's not unrealistic to have that much R value. Okay, so to figure out the R value of this wall section here, and this is something you do in civil engineering. So we've got brick, which has an R value of 0.8. Just from that table. There's a 1 inch air gap, R value 0.17. That foil face polyisocyanurate, fiberglass bat, which is R19. This is for a 2x6. Normally, if you use a 2x4 to create a wall, the R value is only 13 because there's not as much room for fiberglass. And then there's the drywall. So to figure out the R value of this overall wall, you just add them all up together. It's no big deal. So for some reason they want you to look at the R value at the stud location, and you would replace the R19 with the 6.88, whatever. Okay, so you're losing more heat where the studs are, basically, because this has a lower R value. So calculate the rate of heat loss through the wall of the previous page. If the inside of the house is 75 degrees and the outside is 15 degrees C, we're looking at a wall section that's 8 foot by 8 foot, and the R value is in degrees Fahrenheit, foot squared, per hour per BTU. Or not per hour, but the hour per BTU. So the R value, we're just going to look at it at the main wall section, which is had an R value of 27.7. To use this equation, P equals UA delta T, I need to convert the R value into U value by taking the inverse of it. So it's 1 over the R value. Again, a good insulator is a poor conductor, and we want a poor conductor, a good insulator. So my U value is 0.0361, pretty small number. And we stick that into our equation. 64 is because we've got an 8 foot by 8 foot section, so that's my area, 8 times 8. And then my degrees Fahrenheit is the difference between the 75 and the 15. And we get that we're losing 139 BTUs of heat per hour. So that's another way to talk about thermal energy, is in BTUs instead of joules. That's what engineers primarily use, at least they used to. The last type of energy we want to talk about with math is radiation. So this is basically, we already kind of mentioned what it was. It's the loss of energy through electromagnetic waves, or it could be the gain of energy by electromagnetic waves. If you're standing by a fire, you're absorbing. If you're outside on a cold day, you're losing. And this is just a plug and chug equation. So there's the P power. This is a sigma, the Greek lowercase s, which is Stefan's constant. You don't have to memorize it, just stick it in the problem. A is the area of which we're looking at. So if we're talking about your exposed body area, if you're out in a, on a cold night. This is E, which is the emissivity constant, which basically depends on what the substance is that's radiating the heat. So it might be your skin, or it could be the wood of a fire, or it could be the whatever. This is the temperature of the object, and this is the background temperature, or the ambient temperature. So here we got prior to dressing for school, a student watches the morning weather to decide what clothes to wear. The bedroom is 65. The student's skin is 91.4 degrees Fahrenheit. Determine the net energy transferred from the student's body during 15 minutes spent watching the morning news. Given the skin emissivity is 0.9 and the surface area of the student is 1.3 meters squared. So the area is given as 1.3 meters. The emissivity constant is 0.9. Stefan's constant is given. The bedroom temperature is 65. The skin temperature is 91.4. And the time that we're talking about is 15 minutes or 900 seconds. So once we got this, it's basically just sticking the numbers in, although we do have a little bit of conversion to deal. This is in watts per meter squared per Kelvin to the fourth. We do need to convert our Fahrenheit into Kelvin, which I'm not going to worry too much about. We'll let the PowerPoint do that for us. Okay, so they go ahead and figure out this temperature. Now to the fourth power, be a lot easier. You should have a caret button, a little bent. It's hard to describe. A little caret button to bring numbers to a certain power. So you're going to use a button and then hit that caret button to the fourth for your temperature. So we notice that they convert them into Kelvin. Notice that they're not really that far apart when they're in Kelvin. They're only 15 degrees apart in Kelvin. So basically plug in the numbers. And you get 103.9 watts. That's the rate at which you're losing energy. And then to figure out the heat, the total amount of heat lost, P equals Q over T, or delta T. This is Q equals P delta T. Plug in our power, which was what we just found above here, which is roughly 104 times 900 seconds. And again, this is in watts is in joules per second, so this needs to be in seconds. And you get 93,500 joules. So that's how much the energy. Now that was just the energy lost due to radiation. They also convected heat away, and they also conducted heat away to anything in contact. So you're losing energy all the time, which is why you need to constantly resupply yourself with energy. Otherwise, if you run out, you're dead. So these are some applications of radiation energy. So here they're reflecting the radiant energy from the sun onto a pot of water. This is what it is. It's focusing the water, the sunlight onto a container of water which boils and turns a steam turbine. This is a solar collector as well. No idea what this is. I'm not really sure, other than a skyrise building. Here, I guess they're heating the pool water with sunlight. Don't know what's going on here or here. Geothermal energy is another way we can grab energy. Not really sure why they're introducing that here. But anyway, that's it for today. Work on 1.3.3, I believe it is.